1995 E1. This is a very long cylinder and they've given us a cutout here. Radius is lowercase a. And it tells us that it has a positive charge distributed throughout the volume. But if you're outside, it'll be charge per unit length lambda. All right, so for part A, use Gauss's law to derive an expression of the electric field E outside the rod. So Gauss's law has us start in the usual place of Q enclosed over epsilon naught equals E dot dA. And if we have our Gaussian surface to be a cylinder that wraps around the cylinder that was given to us and have it be concentric, unlike my picture, which is not concentric, my apologies, then the radius R, as long as we walk around this curved part here, we don't care about the caps. The curved part here, there will be the same distance R from the cylinder so that the electric field will be constant and it can come out of the integral. Remember, that's the entire point of the Gaussian surface, is to pick it so that the electric field is constant all over the surface. It can come out of the integral, and then we only need to worry about the surface area of that shape, which in the case of a cylinder is 2 pi lowercase r L. And then the Q enclosed, they told us, has to do with charge per unit length. So we'll have to divide this guy by length, and that will get us our charge per unit length of lambda. So substituting each of these guys into here and solving for the electric field. So E2 pi r L, and then the L's will cancel. And the electric field we can solve for by bringing 2 pi r over, so then we will have E lambda over 2 pi epsilon naught 1 over r. And this should look exactly like what we talked about in the notes for a wire, a really long wire of charge. All right, part B. On the diagram below, we have a cross section of the rod, so we putting our eyeball on the end here and looking down the axis of the rod. Sketch the following: equipotential lines in the region outside R greater than A. So this is probably not going to be very good, but what they want to see are concentric circles. So we'll have that, and then we'll have this. I won't even bother trying to do dotted lines anymore. They're supposed to be concentric circles. Now the electric field lines should be arrows that point away from the surface. And they don't tell us anything about a negative charge, so the electric field lines will be pointing away from it, and they should also be symmetric, and you're going to need to have at least 4. If you want to have more than 4, then I would recommend 8, because however much you give it, it needs to be symmetric. All right, part C1. So in the diagram above, we have point C that's on the surface, a distance A, and then we have point D over here that's a distance 3A outside the rod. And for some strange reason, they tell us that the angle between them is 90 degrees. That's not relevant for this part at all. That's just extraneous information that's going to confuse you, because then they start talking about potential difference and work. Those are both scalars. The directions are irrelevant. If they wanted to talk about the electric field and perhaps force, then we would care. But they aren't. They're talking about energy kind of things. All right, potential difference. So C part A. VC minus VD. So we're going to go from D to C, because it's always final minus initial. So the first guy minus the second guy is actually the last guy minus the first guy. So Then over here, we're going to need to have the relationship from where D is at 3a, so then this will be at radius of 3a, and then this will be at radius of a, and that's for the electric field dot dr. And now you're going to need to use your answer from part A. So we'll have VC minus VD on this side, and we will be integrating from 3a to a of lambda over 2 pi epsilon naught dr over r. The entire front part of this is just a constant. It goes along for the ride, and we're integrating dr over r. The integral of that will be natural log 2 pi epsilon naught natural log r 3a to a, and don't forget that minus sign. That minus sign is going to be important. And then on the left side, we're just talking about the potential difference between C and D. All right, so the fun thing that we can do with the minus sign and our limits is that we will use the minus sign to flip the limits. So then we have these limits here. And then we have ln of 3a minus ln of a. And using the rules of the logs means that we get to divide by the insides. So this will be ln of 3a over a. And hey, a over a cancels out. Don't forget your coefficient. I haven't forgotten that. I just didn't want to rewrite it because writing with this thing is kind of annoying. So we'll have lambda over 2 pi epsilon naught ln of 3. All right, part 2, which I haven't given myself a whole lot of space here. It says the work required by an external agent to move a charge plus Q from D to C. All right, so the change in potential energy, so work is going to be the change in potential energy, and that's going to be Q change in voltage. Well, we just found the change in voltage. So the work is going to be Q times lambda times the natural log of 3 all over 2 pi epsilon naught. Now, if you're looking at this and you're saying, hey, wait a second, I used my answer in A as my starting point in C, and then I used my answer in C1 as my starting point in C2, what if I got this guy wrong? Well, that is a concern. However, the way they've set up their answer keys, if you correctly substitute whatever you got in A into C, they'll be happy to see that. So even on this year's test, if you say you use whatever you got in part A in part C inside the integral, and then you will integrate 1 over r, they'll be happy to see that. Or if you have not 1 over r but r, then you come over here and you say, well, now we're going to integrate r, they will still be happy about that because what they want to see is that you correctly use whatever you had here later on. All right, for part D, I think I'm going to need more space, so I'm going to have to pause, clear out, and restart. In part D, now we're going to zoom in inside the cylinder, and they're going to tell us that inside we have rho equals rho naught, parentheses, r over a, all raised to the 1/2 power. And now they want the electric field inside the cylinder. Well, for part D, so we can change this from A to a D, and we will start in the same spot. We will go through the same process, except now Q enclosed is not just going to be a ratio divided by L equals lambda. We're going to have to integrate our function of rho that they gave us with volume. And I'm writing OL there for volume. So they gave us a function for rho. And because this is a cylinder, we're going to have to look at the volume element of a cylinder. So the volume of a cylinder is area of a circle times length. And if we take the derivative of the left, that's not an L, that's a V. So the derivative of the left is, and this is volume, remember, not voltage, volume. Look on the right here, L is constant, pi is constant, R is going to be the variable. So we will have 2 pi RL dr. And you should notice this, you should have noticed this already, the surface area of the cylinder and the volume element of the cylinder are closely related. We're just taking the surface area and then multiplying by how much we're going to increase the radius. All right, now they gave us a function for rho, which we're going to substitute in here, and now we have the volume element called 2 pi RL dr, and we'll substitute that in also. So we're going to integrate from 0 to r because we want to stay inside the cylinder, r over a to the 1/2, 2 pi RL dr. This is a mixture of variables and constants. Everything that's a constant, let's bring that outside. So 2 pi rho naught L over the square root of A. Those are all constants. What stays inside is this R times this square root of R. So this will be R raised to the 3/2 dr, and we'll be integrating from 0 to R, and that will get us the enclosed charge. Now, as we do that, this integral over here will turn into here. I'm just going to call that K for the moment. We'll come back to that later. We'll have K and then R raised to the 5/2 divided by 5/2. Increase the exponent by a value of 1. Divide by the new exponent, and then we'll go from 0 to R. The 0 is going to cancel out, and we will just be left with R. So this is going to be our integral, and we're going to substitute that back into Gauss's law along with the surface area to solve for E. So what is that going to look like? Well, this K here that I didn't want to bother rewriting is all of this junk. So on the left side, we will have 2 pi rho naught L R to the 5/2 all over epsilon naught square root A, E, and then 2 pi RL on the right side. And we can cancel some things out. So the 2 and the pi and the 2 and the pi, and that L and this L, and this R is a 2 over 2R. So we have a 5 over 2 and then a 2 over 2. And using the rules of the exponents, that's going to turn this guy into a 3/2. So what does that make our equation end up looking like, since I've now canceled pretty much everything on the right side? What survived on the left? Well, we have a rho naught. We have an R raised to the 3/2. And on the bottom, we have epsilon naught and the square root of A. Oh, wait a second. And we also have this 5/2 here. This 5/2 turns into a 5/2 down there, which turns into a 2/5 once we flip the exponent over. So we have 2 rho naught R to the 3/2 over the quantity 5 epsilon naught square root of A.